In this video, we'll be talking about software-defined networking. Let's first look at network devices. Traditional network devices are individually configured. If you're given a network device, it contains two planes, a control plane and a data plane. The control plane contains multiple components, including control logic, a storage system, and logic to implement a forwarding decision. The forwarding decision is sent to the data plane, which then controls the flow of packets for the network device. Notice that the control plane and data plane both exist within the network device. This can lead to vendor lock-in. So different devices can be designed to use specific protocols. Routers can use routing protocols such as BGP or OSPF. Switches can use protocols such as ARP. Now, if you'd like to divide a network device among multiple tenants, you use virtual LANs or VLANs. VLAN segmentation is quite difficult and cumbersome. In fact, many devices these days have a VLAN limit of 4,000, which may be difficult when you have multiple tenants in a large data center. Thus, in traditional network devices, it's difficult to implement your own dynamic logic as the need arises. So now we can talk about software-defined networks. Software-defined networks is a new architecture to manage and control network devices. Now you have decoupled control and data planes, so they don't exist in the same device anymore. In the data plane, we have forwarding devices such as switches and routers, and in the control plane, we have a network operating system as well as network applications. The network operating system and applications are now centrally managed and can exist outside of the forwarding devices. And the network applications can be used to dynamically control forwarding decisions at each device. Let's look at some of the interfaces that SDN uses. The forwarding devices or data plane can consist of SDN compatible routers and switches. The interface between the forwarding device and the network operating system, also known as the southbound interface, can consist of a number of protocols. And then we have the SDN control plane consisting of the network operating system and the network applications. The operating system can provide multiple services to network applications, including topology information, inventory, statistics, and host tracking services. Network applications can connect to the network operating system through the northbound interface and can use different APIs, including a Java or a RESTful API. Finally, the network applications can implement high-level logic that will trickle down to the forwarding devices. So you can have applications that do traffic management that can be responsible for provisioning or subnet management. Let's look at an example of a SDN packet flow. When a packet arrives at a forwarding device, the forwarding device can consult the network operating system to choose an appropriate network application to handle that packet. Once it receives that information, the forwarding device can send the information to the next forwarding device in the route. Similarly, this can go on for all of the forwarding devices in the network. Now, here's the example of multi-tenancy in SDN. In our previous examples, we looked at only a single network operating system and a series of network applications tied to that network operating system. In a multi-tenant architecture, you can have multiple network operating systems and network apps. A forwarding device can receive a particular packet identified to be of a particular tenant and choose the appropriate network application from the appropriate tenant to forward the message. Similarly, for the other tenant, they can consult the network operating system for that tenant and the applications for that tenant. Now let's take a look at how packets are transmitted in SDN. So given you have a physical server which has a number of VMs in it, and the physical server is connected to the physical network through the network interface card or NIC. We also have Open vSwitches. These are basically software programs that are running in the physical server to handle network traffic using SDN. Now, an application needs to send a data stream from one server to the other, and that is represented as the application data stream packet. As the application data stream gets processed in the operating system within the virtual machine, there would be headers that are added by the TCP stack running inside the virtual machine. Now, the virtual NIC, which is aware of the software-defined network implementation in this example, will add an additional layer of encapsulation on this packet. And finally, the physical network will add the TCP IP and L2 headers required to route this packet through the physical network. As it reaches the destination physical server, the process is reversed, and then the application is able to receive the data stream. Another topic on SDN is how isolation is implemented in SDN. We can think of this as a number of overlays. Now, we have the physical network, we have machines that are running on a hypervisor, and on the network overlays, we would have a network of virtual machines and the corresponding network devices such as virtual switches, firewalls, etc. Now, these can be overlaid over the physical network since all of the routing is taken care of by SDN.